Alright, so today we're going to be talking about something called extreme values. And so let's just get started. So first we're going to be talking about something called global extreme values. And so what global extreme values are is, and it's pretty intuitive. Basically, there's two types of global extreme values. First, it's called an absolute maximum, and then the second type is something called an absolute minimum. And an absolute maximum is defined as any value c. So a maximum exists at a point c if at point c f of c is greater than or equal to any value of the function at any point x. And then similarly, an absolute minimum is defined as a point c where f of c is less than or equal to f of x for all values of x. And basically, all this is saying is an absolute maximum is the largest value the function can have, and an absolute minimum is the smallest value a function can have. And sometimes, like, these absolute maximums, minimums don't really exist if we're talking about an unbounded interval, right? So if we're looking, like, let's just, for example, take the function y is equal to x squared, right? We know y is equal to x squared looks something like y is equal to x squared looks something like this, right? Where I need to get this straight. Yeah, we know y is equal to x squared looks something like this, right? Where, oh my, okay. Well, basically, y is equal to x squared has this U-shaped sort of structure, and there's no real maximum, but there is an absolute minimum at 0.00, and that's basically what we're looking at. But what's more interesting is um, this theorem called the extreme value theorem. So we have this theorem called extreme value theorem, and that basically states that if a um, if a function f is continuous uh, on the closed interval a comma b, and it has to be closed, um, then f has a absolute minimum and an absolute maximum. So think about why. We need the idea of, like, f to be contiguous, and we need a closed interval, because let's say we're dealing with an open interval, right? So let's just again go back to our little, like, U-shaped curve, right? And we have the interval between a and this point a and this point b, but, like, b is not included right now. We do have this minimum because minimum is between a and b, but, like, our maximum is kind of undefined, right? Because we know that point b is larger than whatever, like, largest point, but point b is not in our interval, because if we had an open interval and we're looking at, like, a and b where b is not included, now we can't really define a maximum, right? Because as we're heading towards b, our value gets larger and larger, but um we can't really say one single point is our maximum. And so we need the notion of a closed interval to really make the statement true. And similarly, if f was not contiguous, and we can just say that, oh, we have a function that has a discontinuity at b, and even though we have this closed interval that we're worried about, f is not defined at b, and it's really just the same case as before, with the argument that we made that as we're approaching b, our value keeps getting larger, but we can't really come up with a numerical maximum in that case. So in order for the extreme value theorem to hold, we need to make sure that in that interval we're looking at, f is contiguous and f is and the interval is closed, and then we're guaranteed to have an absolute minimum and an absolute maximum. So realistically, like these theorems are pretty like simple. They just say that, oh, in if you have a function and you have some interval over which the function is like defined in all the values, then you're gonna have a maximum and a minimum in that situation. So to just hammer this argument across, we can just go over some examples. So let's say that we have a curve that looks like this, right? And the interval that I'm worried about is this. So this is point B and then this is point A. So in this point, we can see that, oh, around here is the lowest sort of value, and that will be our absolute minimum. So I'll just call this absolute min. And then over here at point A is the largest value our function takes on in that interval. So this will be our absolute maximum, right? Um, and then likewise, if we have another curve that's just continually decreasing like this, right? And then this is point B, this is point A, we see that this over here is our absolute max. And then over here, this is our absolute min, right? And I think it's kind of obvious like now that with any sort of function we draw, and if we just create these intervals like that, if we have a graph of that function, we can easily find out where absolute mins and absolute maxes are. And so these are known as extreme values because in a lot of applications, it's very important to find out where some maxes and mins are because they provide useful properties. And so we spend a lot of time actually discussing how we can find it. And before I get into the ways of finding these values uh, analytically, there's also two other extreme values that are very important. And let's just cover those extreme values. And so these are known as the local extreme values. And we have again two types of local extreme values. We have a local maximum and we have local minimas. So unlike absolute maxes and absolute mins, where we're worried about just the value at which the point at which we have the highest ever value or the lowest ever value, local minimums and maxima are defined a bit differently. So point C is the local maximum if f of x is less than or equal to f of c for all x in some interval around c. And similarly, a point is a local minimum if f of x is greater than or equal to f of c, again, for all x in some interval around c. So the only thing we changed in our definition of a local min to local extreme values to global extreme values is the fact that we're only worried about an interval around the point instead of like just the whole function itself. And essentially that's saying essentially that's just saying like if we have some like hill or like valley like this, so if we look at this point in the interval around the point, this like point d prime is the lowest value, right? And then similarly over here, this point e prime has the highest value in the interval around the point, so we can call this a local maximum and local minimum. And the fact that it's local is more like accurate when um, we have a function that's like decreasing on this area and then increasing over here. So these are clearly not going to be the global mins and global maxes, but they are going to be local mins and local maxes because they satisfy the definition above. And so now let's just look at a another like toy graphical example where we classify points as local mins, maxes, global mins, and maxes. So let's draw out a similar curve that kind of looks like this, right? And then I'll have this. Okay. So we're only worried about the interval defined from here to this point. So let's just call this point B, and let's call this point A, and we're only worried about the interval between that. And we know that, let's just say that the function is defined and contiguous on all of this interval. We can call this this point an absolute minimum because of the fact that it's the lowest, the function takes on its lowest value at this point. Over here, this point, we can call it a local max. And it can't be a global max because this point is clearly larger, but in the immediate interval around it, it takes on the biggest value. And by similar argument, that point over here is a local min. And like I alluded to before, over here is the largest value the function takes on, so that point over here is a global max. And then over here, because it's an endpoint and it's decreasing, this is the lowest value it takes on, so this is now a local min. And I think, notice how, like, in this example, we see something very interesting. Our local mins, or any of our extreme values, occur in three different cases, right? So we notice how our extreme values are either at like endpoints, right? Both the endpoints happen to be extreme values, so both these two endpoints are extreme values. They're at points where the derivative is undefined, so this is kind of like a cusp, right? Like just inverted cusp. So over here, if this function was f prime of x is undefined. Or if we were to like kind of draw out the slope over here, we can kind of draw out a horizontal line, right? And so this f prime of x or c or whatever at that point is 0. And this is not a coincidence. And this kind of like motivates how to find extreme values analytically. So we kind of saw like through the graphically, like it's kind of easy to find our extreme values, right? It's not very like hard of a concept. But how do we now go from like a random analytical equation to finding the extreme values relating to the equation? And so what I defined above is the notion of a critical point. So critical points. Critical points are wherever the derivative of function does not exist, or wherever the derivative of function is 0, right? And we kind of saw in the previous case that endpoints, like so like if I were to just draw the toy example like I had before, at endpoints of the interval, our derivative does not exist, right? Because the limit from the right hand side, we can't really define that limit from the right hand side because we only have the function defined at one side, and so our derivative cannot exist at that point. And so endpoints are critical points, and then in the other example we had like a cusp, right? Like something like this. And so this derivative at that point does not exist as well. So that was a critical point. And our final case is where the derivative is 0. And so that's a critical point. And critical points are interesting because the fact is, critical points are the only candidates for extreme values. So this is very key over here. Now we've just come up with a structured way to find extreme values, which is find critical points And then once we found the critical points, observe behavior around those points. And once we take these two steps, that's the only thing we need to find out the extreme value of any function. And to just reiterate, our critical points are the endpoints if we have a closed interval, right? And they're at any point where the derivative does not exist and the derivative of the function is zero. So if we're ever told to find the extreme value of a function, we first have to calculate all the critical points. So we just find the endpoints. So if the function is just defined between a and b, it's a comma b plus we find f prime and we just find out wherever f prime doesn't exist and f prime is zero, obviously in that interval, and then all of those like different points happen to be critical points. And once we have found those critical points, we then do this observation step, and then the observation step will help tell us whether this certain point is a local min, local max, global min, global max, or it's none, which is possible. It could not be a global min or max, and it could just be a red herring for a critical point. And that's a lot. So let's actually get into a lot of examples to find out um, how to systematically find extreme values. So we'll go over some examples. And so the first one is this function f of x is equal to x to the power of 2/3 on the interval -2 comma 3. And so the first thing we need to check is whether this function is defined in this interval. And f of x is defined on all reals, so we don't have to worry about it being contiguous or not in that interval. And so let's find f prime. F prime of x is simply 2/3 times x to the -1/3, right? And now we need to find out whether f prime is 0 or undefined. So if I rewrite this as this equals 0, this is clearly never 0, but it is undefined. And it's not 0 because if I multiply out this case, then I get like 2 equals 0, and that cannot be possible. So this function's never 0, but f prime of x undefined at x equals 0. So our critical points are x equals -2, x equals 0, x equals 3, right? Because -2 and 3 are the endpoints, and x equals 0 is where f prime is undefined, right? And so now, how do we actually go about how do we go about classifying each of these points as like what kind of minima or maxima are they, or whether they're not or not? So one thing that can do is have this little number line. So -2, 0, 3. We have to find f of x in these cases. So f of -2 is simply so at -2, the value of f of x is the cube root of 4. At 0, the value is 0, and then the value at 3 is simply the cube root of 8, which is equal to 2, right? And then we need to sort of see if these points are minimums or not. And the way that we gauge if they're minimums or not is we have to look at how their derivative is changing. So we have a number line that shows how x is changing, and now we build a number line of how f prime is changing at those points. So at -2, at 0, and at 3. And we're only really worried about the sign of those of f prime, and we'll see why in a second. So we calculate f prime over here. So between -2 and 0, this is all negative, right? And the cube root of a negative number is going to be negative. So in this interval, f prime is negative. So I'll just draw that as a decreasing arrow. And then once I query positive values, our cube root is positive, right? So then it becomes f prime is positive, so I can draw an increasing value. And that must mean that at 0, which was the critical point, our sign of our derivative changed. So our function was initially decreasing, as we saw here, and then started increasing. And whenever a function is decreasing and then starts increasing, we know that at that point where we have a change, it's like an inflection point, right? Or not an inflection point, that's something else. But it's a point where our sign changes. And so after 0, it must mean that our value of f keeps getting larger and larger, right? And so must be a 0 must be a minimum, right? And we see that 0 is less than all of these other points in the critical point. So we know that 0 is an absolute minimum. And we found that out because of the fact that we analyzed how f prime changes. Now we have to look at these last two critical points. We know that at the endpoint we have x, like before the endpoint at 3, our function was increasing. And so that must mean that whatever value we have to the left of 3 is less than what we have at 3. So that must mean that this is some sort of maximum. And then similarly, to the right of -2, our function is decreasing as well. And so this is also some sort of maximum. So both of these are maximums, but one of them is going to be a local max, and the other one's going to be a global max. Because you can't have two global maxes if their values are different. And we know that cube root of 4 is less than 2. So at point 3, we have an absolute maximum. And at point -2, we have a local minimum. And that's how we have sort of calculated all the extreme values of this function. And so notice how really there's two things that are very key to finding the extreme value. We must find out all the critical points, which is pretty simple. After we find f prime, we just find places in the interval we're worried about where it's undefined or 0. And once we've found those critical points, we find the function's value at those points like I did over here. And then we have to sort of analyze the behavior of how the function is changing around the points. And we do that by analyzing the derivative of the function. And by analyzing how the function is changing, we can kind of find out whether the function is a local min, or whether those points are mins or maxes. And then to classify whether something is an absolute min or an absolute max, we just simply look at the values, and the min that has the lowest value will be an absolute min, and the max that has the highest value will be an absolute max, and everything else is a local max, right? And so let me touch on the step of observing how f prime changes. So let's say we have this like critical point A, and if we note, there's really just like there's really just like a few cases, right? If before A we saw the functions increasing and then we saw it was decreasing, we can kind of know that our function is going to be acting like this, right? And so A will in this case be an absolute max, or it will be a maximum, right? To find out whether something's an absolute or a local, we have to find out all the candidate maxes and compare, and the one that's an absolute max is the one that has the highest value. Consequently, or on the contrary, if we had this behavior like we saw, then A will be a minimum. But if you have like this behavior, then the function's just gonna be something like this, where it becomes 0 for a while, but it just continues increasing. So it'll be neither. And if we had two like downwards after A, it will just be the opposite, right? So it's only at these like phases where we have like a valley or a hill, through the observation of the derivative, that we can kind of decide whether it's a max or a min. And to really like hone this down, let's do another example. So let's say we have another function, f of x is equal to 1 over square root of 4 minus x squared. And now we're not worried about a specific interval. We're just going to do it in the whole domain, right? And so, like, because we're not given a specific domain, the first thing that we should probably do is find out where this is defined. And we know that the square root only takes in positive values. And 4 minus x squared, that means we must have the interval where 4 minus x squared is greater than or equal to 0. And so this is 2 minus x, 2 plus x. And then so we have negative 2, and then we have 2. And then we know that if we take in a value below 2, our function is negative. In between 0 and in between negative 2 and 2, it will be positive, and then it will be negative here. So in reality, the domain of this function is between 2 and negative 2. So that's the domain that we're worried about, and it's exclusive of negative 2 and 2 because we don't want the denominator to be 0 as well, right? That means that in this case, negative 2 and 2 cannot be critical points because it's not defined in the function itself. Now let's go finding f prime of x. So I'll rewrite this original one as 4 minus x squared to the power of negative 1/2. So f prime of x is just negative 1/2, and then we get 4 minus x squared to the power of negative 3 over 2, and then through the chain rule we have minus 2x over here. These 2's cancel out, and so we get x times 4 minus x squared to the power of negative 3 over 2 is equal to f prime of x. Now where is f? Now to find the critical values of these points, or to find the critical values of this function, we must find out where this is 0 or undefined, right? Undefined is basically where this denominator, because of this negative term, is 0, and that's just going to be the same points as negative 2. So f prime of x undefined at x is equal to negative 2 comma 2. But these 2 points are not in our domain, so that's not in here, so we ignore it. And f prime of x is equal to 0 when clearly x is equal to 0, right? When x is equal to 0. So it turns out that our only critical point in this case is x equals 0. So that's our only candidate. So let's draw out our handy number line. Oh, sorry, this is f. This is f, and then this is 0. And then we'll see how f prime behaves in that same number line. So before x is 0, f prime of x, this is going to be, well, let me just rewrite it over here for clarity. We know that f prime of x is equal to x times 4 minus x squared to the power of negative 3 over 2. So when x is less than 0, this term's negative, but this term is positive because we're only worried about the interval from negative 2 to 2, right? So in reality, like, we have a hard cutoff at negative 2 and 2 because afterwards the function is not even defined. So in that range, because this term is negative and then this term is positive, f prime is going to be negative, hence we're going to draw something decreasing. Now, similarly, between 0 and 2, this now is positive, and this is also just positive, so it's going to be increasing, right? So we know that the point at 0 is a minimum because of this valley sort of structure. So we know we have a minimum over here, and thankfully, because this is our only critical point, we don't have to worry about really calculating what the value at 0 is, even though it's kind of simple. It's just 1/2 if you plug it in, because there's no other minimums to compare to. And so because this is our only minimum, it must be an absolute minimum. We don't have any other candidates. So we can say that we have a absolute minimum at x equals 0. And there's no maximums in this case, and that makes sense because of the fact that we don't really have a closed interval. This is an open interval of -2 to 2, and so no maximums, and this is our only extreme value. And let's just do one final example. And here we have a piecewise function. So f of x is equal to 5 minus 2x squared, where x is less than or equal to 1, or it's x plus 2 when x is greater than 1. So when we have piecewise function, we must see whether the derivative is, or whether the function is defined at x equals 0, right? Or, well, we must see what the behavior is when x tends to 1, and if the derivative is actually defined at that point. So let's just first find f prime of x. So f prime of x is equal to minus 4x and 1, and then remove the equality. And at x equals 1, clearly from the right hand side, our one-sided derivative is -4, and then from the left-hand side, or sorry, this is the left-hand derivative. From the left-hand derivative, it's -4, and the right-hand derivative is 1. And 1 is not equal to -4, so the derivative at x equals 1 is not defined because the right-hand, left-hand derivatives do not match. And so to find out the critical points, we know on the interval of x being greater than 1, our derivative is never 0, so there's not going to be any critical points there. But -4x is equal to 0 when x is equal to 0, and that satisfies this domain constraint. So that is a critical point we're worried about. And then x equals 1 is a critical point because of the fact that our derivative at x equals 1 is not defined, since our left and right hand derivatives differ. So in summary, we found out that our critical points are x equals 0 and x equals 1. So let's draw out our number line. We have 1 and 0. Those are the points of inspection. We're going to see how f varies, and we're going to see how f prime varies. When f prime is greater than 1, we know that f prime of x is just 1, so this will be positive. Between 0 and 1, it will be negative because x will be positive, and then this whole term will be negative. And then when x is less than 0, -4x will be a positive value. So we'll have something like this. So that means the point at x equals 0 is a maximum. So we can say max over here. And then the point here is a minimum. Again, we only have one max, one min. So we know that it must just be the global max, global min. If there are multiple maximum candidates, then only one of those, or I mean, it is possible multiple of them are global maxes and mins if they have the same value, but we could have local mins, and so in that case, we would have to calculate the value of f at those points, and then see which one's the greatest or least. But let's just do it for the sake of completeness. F of 0 is simply 5. F of 1 is simply 1 or 5 minus 2, which is 3. Now 3 is less than any other candidate for min, so we can, because there's no other candidates, so x equals 1 is a, or oh wait, actually, my bad. In this case, both x equals both of our mins and maxes cannot be global mins nor maxes because of the fact that we're not looking at a closed off domain, we're actually looking at the entire domain, right? And so the fact that f prime continues to decrease on this part and f prime continues to increase on this part after 3 or after x equals 1 means that means that any value following x equals 1 will be greater than 3, and it will keep going on and on, keep growing unboundedly, and similarly will keep growing towards negative infinity unboundedly after x equals 0. So that must mean that this max over here is not a global max, and similarly this max over here is not a global min, because of the fact that we have this unbounded growth on both sides. So to reiterate, x equals 0 is a local max, and x equals 1 is a local minimum. And so, in summary, to find the extreme values of any function in a systematic way, we must find the critical points, right? And so, if we were given a closed interval, the critical points include those two endpoints, as well as the fact that they always include wherever f prime is 0 or undefined. Once we have all those critical points, we must analyze the behavior by drawing out how f prime is acting around the interval of those points. And then once we've found out the max and mins, our final thing is to classify them as local or global mins and maxes. And that we classify by just making sure if something's a global max, it must be the highest value the function ever takes on. And because of the fact that we're looking at an unbounded interval in this scenario, and the fact that we have growth towards the positives on the positive infinity side and growth towards the negatives on the negative infinity side, in this case, there's no global mins or maxes. But, like the toy example of y is equal to x squared, we clearly have a global min. And that's because f prime after 0 continues is positive on both ends. So this is the only min, and we don't get a value below it. Hence, it's a global min. So hopefully this kind of helped find out how to calculate extreme values. And it's really just a matter of being careful and reasoning well.